No, good morning everyone. Now we'll start with the root locus, continuing the previous module. Now it appears from our previous discussion that the root locus can be obtained by sweeping through every point in the S-plane to locate those points for which the angles, as we have described earlier, add up to an odd multiple of 180 degree. Although this task is tedious without the aid of computer, the concept can be used to develop the rules that can be used to sketch the root locus without the effort required to plot the locus. So once the sketch is obtained, it is possible to accurately plot just those points that are of interest to us for a particular problem. So, as clear from this statement that instead of going to test each and every point whether it lie on the root locus or not, there are a certain set of rules. If we follow certain set of rules, then definitely we can obtain the root locus. That is that concept we have to take into consideration, that concept only, that the points for which the angles add up to the odd multiple of 180 degree, and we apply certain rules, and after applying certain rules we get the certain points, and that points will give the root locus instead of going of checking each and every point in that. So there are certain rules, that is 5 rules, which allow us to sketch the root locus using the minimal calculations. The rules yield a sketch that gives intuitive insight into the behavior of the control system. So what we do, first we define these 5 rules. Like the first rule is the number of the branches, second one is the symmetry, third one is the real axis segment, fourth one is the starting and the ending point, and fifth one is the behavior of the infinity. So we will discuss these rules one by one, and once we know these rules, we can obtain the root locus of any transfer function. Now first start with the number of branches. Now how many branches are there in this case? As we have seen in the earlier example also, we have the 2 poles, and for that 2 poles the 2 branches would be there, that is one move in upward and second move downward, as we have discussed in the previous examples also. So each closed loop pole moves as the gain is varied. If we define a branch as a path that one pole traverses, then there will be one branch for each closed loop pole. So this defines our first rule, that is our first rule then defines the number of branches of the root locus. The number of branches of the root locus is equal to the number of poles. If we have number of poles, then the number of branches in this case would be 2, that we have seen in the previous example also. That is, the number of branches is equal to number of closed loop poles. So this is the first rule. So first point is the number of branches, that is number of branches of the root locus equals to the number of closed loop poles. Now second one is the symmetry. These complex closed loop poles always exist in the conjugate pairs. That is, it always exists in the conjugate pair, as we have seen in the earlier example. That is, in this example you will see that these exist in the conjugate pair, that is 5 plus j 2.24 minus 5 minus j 2.24, then we have this one. So these actually exist in the conjugate pairs. These exist in the conjugate pairs. So with these conjugate pairs we don't have the complex coefficients, that is which can be proved. That is, if the conjugate pairs are there, then no complex coefficients are there. So if the complex closed loop poles do not exist in the conjugate pair, The resulting polynomial formed by multiplying the factors containing the closed loop poles would have the complex coefficients. That is, it would have the complex coefficients if the conjugate pairs would not be there. So, physically realizable systems cannot have complex coefficients in their transfer functions. So, if we see the system, physical system, they don't have the complex coefficients. That is, this j term would not be there in that very case. So, the one observation from that is that the root locus is symmetrical about the real axis. That is, they exist in the conjugate pairs. So, the root locus must is the symmetrical about the real axis, and they must exist in the conjugate pairs. If they do not exist in the conjugate pairs, then definitely they would have the this complex coefficients, and these are not physically realizable systems. Now come to point number 3. Now next is the real axis segment. So let us make use of angle property of this angle property of the points on the root locus to determine where the real axis segments of the root locus exists. That is, we have to use this angle property of this root locus to find the real axis segments of the root locus, that where the real axis segments of the root locus will exist. Now let us suppose the pole, let us consider this figure. Let us consider this figure. In this figure, we have poles and zeros of general open loop system. Poles and zeros, that is P1, P2, P3, P4, these are the poles, and these are actually the zeros of the open loop system. Now, if an attempt is made to calculate the angular contribution of the poles and zeros at each point, that is, if we want to get the angular contribution of poles and zeros at each point, that is P1, P2, P3 and P4 along the real axis, the following observations can be made. Now the first observation is that at each point the angular contribution of the pair of open loop complex poles or zeros is equals to 0. That is, if we see the angular contribution of the open loop complex poles, a pair of open loop complex poles, that contribution is 0. That is, let us suppose that we have a pole this and we have a pole this, and if we see the contribution of this angular contribution, then we have the, here we have positive angle, here we have the negative angle. So angular contribution of this of two poles in this case would be equal to 0. That is, angular contribution of complex poles in this case would be equal to 0, because this is angle, positive angle, and this is the negative angle. This one is the negative angle, this is the positive angle. So net angular contribution of these pair of poles, that is complex poles, is equals to 0. That is the angular contribution of open loop complex poles, open loop complex poles or zeros is 0. Okay. Now come to second point. Now in the second point, now come to the second statement. As per the second statement, the contribution of the open loop poles and open loop zeros to the left of the respective point is equal to 0. That is, the contribution of open loop poles and open loop zeros to the left of the respective point is 0. That is, the contribution of the open loop poles and open loop zeros to the left of the respective point is 0. Now, to prove that statement, now let us consider this. To prove that statement, let us consider this figure. In this figure, you will see that we have a pole at -1, -2 and zeros at -3 and -4 in this case. Now, if we see that if we let us suppose that we are at the point this within -1 and -2. Now, the contribution from this pole, that is -1, to the that is the angle from this -1 to this point, it is equals to, that is this one and this one, from to this point, that is where we want that, and to the 0. So this angle in this case is 180 degree. That is, these are opposite to each other. As a result, the angle is 180 degree in this case. Now, let us suppose that we want to see the angular contribution of -2. So the angular contribution of -2 is to this point and to the 0. So this is 0. Now, this is the angular contribution from pole to any point where we want to see, or we want to observe. So this is the we want to see the angular contribution. Now, third one is -3. So -3 is also to the left. So one is to 0 and one is to this point. So it is also 0 in this case. Similar is with the case with the -4 also. So from this, what we conclude? We conclude that the angular contribution of whatever these poles are zeros to the left of a particular point is angular contribution in this case is 0. Okay. So the contribution of open loop poles and zeros to the left of the respective point is 0. That we have seen. That is, from this the contribution would be, the angle would be 180 degree. So it is a odd multiple of this. So contribution would be there. However, in case of -3 and -2 and -4, the contribution in this case would be 0. So we cannot have this odd multiple. This cannot be proved in this case. So only contribution of the pole is the pole -1 if the point lies between -1 and -2 in this case. Okay. So the conclusion of this is that the only contribution to the angle at any of the point comes from the open loop real axis poles and zeros that exist to the right of that particular point. That is, only contribution will come from the points from any pole or zero which is at the right. If we are at this point, then only contribution is from this. Okay, if that is if the real axis poles and zeros that exist on the right of the respective point, if this is the right of the respective point, then this is the contribution that we are getting only. Okay, now also if we calculate the angle at each point using only the open loop real axis poles and zeros to the right of each point, we make the following observations. The angle on the real axis alternate between 0 and 180 degree. That is that we have seen that we get the angle as 0 and the 180 degree. From this case we get the angle as 0, and for this case we get the angle as 180 degree. So the angle on the real axis alternates between 0 and 180 degree. The angle is 180 for the regions of the real axis that exists to the left of an odd number of poles or zeros. So if we have this angle alternate between 0 and 180 degree. However, let us suppose that we have, so we have repeating the second point, the angles on the real axis that is the first point was that alternate on the angles on the real axis alternate between 0 and 180 degree. Second point was that the angle is 180 for the regions of the real axis that exist to the left of an odd number of poles or zeros. So coming to the first point is that angle alternate between 0 and 180 degree. Okay. Now the second point is that the angle is 180 degree. Angle is 180 degree for the regions of the real axis that exist to the left of an odd number of poles and zeros. That is, if we have odd number of pole and zeros and we analyze that point, that point the odd numbers would be on the left, odd number of poles or zeros would be on the left, then definitely we get the 180 degree angle. Now how this can be proved? Now first point is that angle between 0 and 180 degree. Now second is that if we have the odd number of poles and zeros to the left of the point, then the contribution would be there, then angle would be 180 degree. Now let us suppose that we have these poles, we have 2 poles in this case and 2 zeros in this case. Now let us suppose that this is the point of observation. Now from this we will see that the contribution of all -2, -3 and -4 equals to 0. That is, let us suppose that we want to contribute to -2, that is from this -2 to this point and this -2 to 0 to find the angle. So angle in this case is 0. Similar is the case with the -3 to that point and -3 to this, so the angle is 0, and similar case exists for the -4 to 0 and this, so 0. So in this case the contribution is 0. Now come from -4, -3 and -2. Now come to this point -1. Now from the -1 you can we will see that the contribution from -1 to that particular point, from -1 to that particular point is this, that is from line this to this, and then from -1 point to 180 degrees. So we have an angle of 180 degree in this case, from point -1 to this particular point, that is point of observation, and from this -1 point to this axis. So we have an angle of 180 degree in this case. So we have an angle of 180 degree in this case. So if the point of observation, if we have odd number of poles on the left side of the point of observation, then we will see that the contribution, that is angle in this case, is 180 degree and contribution is there. Now come to the point between -2 and -3. Now if if the point of observation is between -3 and -2 and -3, in this case, that is, the point of observation is -3 and -2. Now from this we will see that we have this angular contribution of 180 degree, that is from this first pole to this point and then pole to 0. So the angular contribution in this case is 180 degree, and again the angular contribution of 180 degree pole, and again the angular contribution of the second pole is also 180 degree from this to this, because we have this point and this. So angular contribution in this case is also 180 degree. So angular contribution in this case is 360 degree. However, the angular contribution by -3 and -4 in this case is 0. So we have an angular contribution of 360 degree. So 360 degree is actually, it is not the odd multiple of this, as we have explained here. It is not the odd multiple of this. So we cannot, so as a result the root locus will not lie within the point -2 and -3. Now come to the point between -3 and -4. To -3 and -4, you will we will observe that for the -1 the contribution would be 180 degree, as we have already observed. That is, let us suppose that point is between -3 and -4. For the contribution of -1 we have 180 degree. For the contribution of this -2 we have 180 degree. Now for the contribution of this -3 we have the 180 degree, and the contribution of this -4 in this case is also equals to 0, because it is to the this point, that is to the right of that is arrow here, and the second arrow is here in this case. So the angle in this case is 0 degree. Now you will see that we have different contributions. That is, this is the contribution for the -1, this is the contribution for the -2, this is the contribution for the -3, and this is the contribution due to the due to this -4. So as per the angular definition, that is zeros, sum of zeros minus sum of the poles, that is sum of the zeros minus sum of the poles, angle of sum of zeros and angle of sum of poles. So sum of zeros in this case, we have only contribution of 0 is 180 degree, and contribution of pole is 180 into 1 plus 180 is 360. So finally we are getting 360 degree minus 180 degree, which is equals to 180 degree. This is the it is opposite. That is, we have to write first the zeros and then first the poles. In this case the contribution of zeros is 180 degree, and the contribution of pole in this case is 360 degree, and again we are getting 180 degree, which is actually the odd multiple of this. So we get the contribution, because this as we have seen that we have the odd number of points, that is poles and zeros, to the left of the point of observation. So same thing happens. So same thing happens when one would be there, the contribution was there, then when we have a point between these two, and only one pole on the left of the point of observation, and if we have two poles on the left, then the contribution was 0 in that very case that we have observed. And if the point of observation would be there, then we have 3 poles and zeros to the left, then the contribution would be there, because we have the angular this condition is satisfied, and this point is on the root locus. So from this observation we can see that on the real axis, so from this following observation can be made in this case, that is on the real axis, for k is greater than 0, the root locus exists to the left of an odd number of real axis finite open loop poles or finite open loop zeros. So if the point of observation is there, and on the left side of the point of observation we will have the odd number of poles and zeros, then in that very case the root locus exists. That is, from this definition we will see that if the point is here, then we have the odd number of this pole to the left axis, so the root locus exists for this point. Here we have the even number of poles to the left axis, so root locus does not exist. Here we have the odd number of poles and zeros to the left, and that is root locus exists for this case. So I think this point is clear, that how the root locus exists in case of real axis segments. That is, this is the angle is between 0 and 180 degree. In this case the angle is 0 and 180 degree, and only contribution is from the if we have odd number of poles or the zeros to the left, that is 1 and 3. So the root locus exists between -4 and -3 and -1 and -2, and not in this point because we have the even number of poles and zeros here. Now come to fourth point, that is starting and the ending point. Now the importance of this point is that we want to know that where the root locus begin, that is where the root locus begin, that is k equals to 0, where the k equals to 0, and end, that is where the k equals to infinity. That is, we want to know that where this root locus begin, that is at k equal to 0, and where the root locus will end, that is k equal to infinite, that is infinite gain in this case. So the answer to this question will enable us to expand the sketch of the root locus beyond the real axis segment. Now let us consider a closed loop transfer function Ts. So let us suppose that this is a closed loop transfer function Ts that we have explained earlier, that is, this is the block diagram of that. So let us consider this closed loop transfer function Ts. So now let us evaluate this Ts for both large as well as small gain. That is, if we evaluate this Ts for the small gain, that is k approximately equals to 0, and for the large gain, that is k is approximately equal to infinite. So we have to see for both small and the large gain, this we have to see that how the transfer function will vary for a small and the large gain. Now if the k approaches 0, that is if we have a small gain, in this case this term is negligible, so this denominator term is negligible, so we are left only with the k and g, dh, dg and dh plus epsilon. This term, this is a very small term and it can be neglected. So from this we see that the closed loop poles at the small gain approach the combined poles of gs and hs. That is, here we see dg and dh. dg and dh are the poles of gs and hs in this case. So the closed loop system poles, if the gain is small k, that it approaches the combined poles of d, g and dh in this case. So from this, that is k approaches 0, k is small, we conclude that a root locus begin at the poles of GS and HS. So they begin at the poles of GS and HS, that is this one, DG and DH, these are the poles of GS and HS. So this root locus begin at the poles of GS, HS, that is open loop transfer function. Now let us consider the case in which the k is large, that is for the high k. For the large value of the k, we see that this term is negligible. For the large value of the k, this term is negligible, so we are left with this term only. So we have ng and nh in this case. Ng is in the zeros of GS and HS in this case. So we see that the closed loop system pole at large gains approach the combined zeros of GS and HS. These are the combined zeros of GS and HS, and we conclude that the root locus ends at zeros of GS, HS, the open loop transfer function. So as k approaches infinite, so this term is the numerator of GS and HS. So it means that as k approaches infinity, so closed loop poles at large gain approach the combined zeros of GS and HS. So it means that as this root locus will start at the poles of this GS and HS and the ends at the zeros of this GS and HS. It will end at the zeros of this GS and HS. So the root locus begin at the finite and infinite poles of GS and HS, and it will end at the finite and infinite zeros of GS and HS. Now let us take the small example that we have taken in the previous case also. That is, here we have, in this case we have the poles at -1 and -2, and zeros in this case are -3 and -4. Using the rule derived, we find that the root locus begin at this point, that is -2. Root locus will begin at -2 and -1, and it will end at -3 and -4. Thus the poles start at -1, -2 and move through the real axis between the two poles. Now here suppose one will start from here, that is -2. One will start from -2 and other will start from -1. That it starts from the two poles and move through the real axis between the two poles, and they meet somewhere between the two poles and break out into the complex plane, moving as complex conjugates. So they break out moving as the complex conjugates, as we have seen in the earlier example also. That is like this one. That is, they start from these two poles, -1 and -2, then meet somewhere and break out into the complex conjugates, as you have seen. Now the pole return at the real axis between the zeros, that is -3 and -4, okay, where their path is completed as they move away from each other and end up respectively at the two zeros, that is one is here and one is here. So at two zeros, that is -3 and -4. So this pole start at -1 and -2, they meet somewhere between these two and then move as complex conjugates. These move as complex conjugate, one is upward and one is downward, and then it has to end up at the zero. So it meet somewhere within the two zeros, that is -3 and -4, and end up at the zero, that is -3 and -4, that is end up in the opposite directions. Now this is all about whatever we have studied, that starting and ending point. It will start at the pole and end at the 0, and this is how it will start and it will end. Now come to the next. Now we apply the rule 4 to the open loop transfer function. Now this is the open, let us suppose that we have the open loop transfer function, and in this case we have the 3 finite poles in this case, that is s equals to 0, s equals to -1 and s equals to -2, and no finite zeros in this case, that is no 0 exists in this case. Now the function have infinite poles and the zeros. Now if the function approaches infinity as s approaches infinity, then the function has the pole at infinity. Now this is very important point. If a function approaches infinity as s approaches infinity, if the function approaches infinity, if let us suppose that function f, if it approaches infinity, then as s approaches infinity, now then function has the pole at infinity. If the function approaches infinity as s approaches infinity, then function has the pole at infinity. Now if the function approaches 0, if the function approaches 0 as the s approaches infinity, as the s approaches infinity, then function has 0 at infinity. Then the function has 0 at infinity. So from this it is clear that if the function has function approaches infinity for s approaches infinity, so it has pole at infinity, and if the function approaches 0 for s approaches 0, then it has 0 at infinity. Now this can be explained with an example. Now let us suppose that we have gs equals to s. It has the pole at infinity. Since gs as s approaches infinity, as we see this, as s approaches infinity, this function gs approaches infinity. It means that it has a pole at infinity, since gs approaches infinity as s approaches infinity. So this is satisfied. So it has a pole at infinity. Second case, that gs equals to 1 by s. Now in this case, if we put s equals to infinity, in this case 1 by s, if we put s equals to infinity, and if s equals to infinity, then in that very case function is equals to 0. So this is that statement is proved that if the function approaches 0 as s approaches infinity, then the function has 0 at infinity. So if gs equal to 1 by s has 0 at infinity, since gs approaches 0 as s approaches infinity. So if we put s equals to infinity, if function is 0, then it has 0 at infinity, and if we put s equals to infinity, and if pole is infinite, then we can say that it has pole at infinite. Now every function has equal number of poles and zeros if we include the infinite pole and zeros as well as finite poles and zeros. So poles and zeros of every function is same. Now in this example you will see that it has 3 finite poles and 3 infinite zeros. We have the 3 finite poles in this case and 3 infinite zeros, which means that poles and zeros must be same in both these cases. So let in this case s approaches infinity. Now let us take this function. Let us instead of using these s plus 1 and s 2, let us suppose that we have s cube in this case. So it is approximated as k divided by s cube, k divided by s into s into s. Now from this previous example, we will see that if we put s equals to infinity, that s equals to infinity, in this case function would be equal to 0. So if s equals to infinity, so this function, this would be equal to 0, the whole of the function would be equal to 0 when s equals to infinity. So it has the we have 3 poles, so 3 zeros at the infinity, so it has the 3 zeros at infinity. So this point is proved here. So since we put s equals to infinity and we get function equals to 0, so it has 3 poles, because as 3 poles would be there, so it has 3 poles at the infinity. So the it has 3 zeros at the infinity, not the poles. So it has 3 zeros at infinity, so number of poles and number of zeros should be same. If we have 3 poles, then it should have 3 zeros at the infinity. So this point is quite clear, that number of poles should be equals to number of poles should be equals to the zeros, if we include the infinite poles and zeros as well as finite poles and the zeros. And if the zeros is not in the in any example, then in that very case, that zeros would be at infinity, and it can be obtained by this. So from this we will see that as we have already said that root locus start at the poles and end at the zeros. So in this case the root locus begin at the finite poles in this case, that is we have the finite poles in this case. So root locus begin in this case at the finite poles. So the root locus will begin at finite poles, okay, and ends at infinite zeros, ends at infinite zeros. So it will start at the finite poles and end at the infinite zeros. Now what are these infinite zeros? We must know these zeros in order to show the locus moving from 3 finite poles, that is we must have these infinite poles, these zeros, to know about the locus moving from these 3 finite poles to these 3 infinite zeros, that is to the these finite poles to the infinite zeros. We must we know the finite poles, but we don't know the infinite zeros. So for the locus running, we must know these infinite zeros. So this rule number 5, this will help us to locate these zeros at infinity, that it will help us to locate these zeros, locate these zeros at infinity, locate these zeros at infinity. So these rule number 5, it will allow us to locate these zeros at infinity. And the second point is that it helps to locate poles at infinity. It helps us to locate the poles at infinity, okay. So this rule number 5 will help us to locate the poles and zeros at infinity. However, in the physical systems we have more finite poles than in the physical system we have more finite poles. We have more finite poles than finite zeros, since the implied differentiation yields infinite output for discontinuous input functions such as step inputs. So the rule 5 will tell us that what the root locus look like as it approaches the zeros at infinity, as it approaches the 0 at infinity, or moves from poles at infinity. So this rule number 5 will tell us. Now the rule number 5, now the root locus approaches the straight line as asymptotes as the locus approaches the infinity. So the root locus approaches straight lines as asymptotes as the locus approaches infinity. Further, the equation for asymptotes is given by the real axis intercept, that is sigma a, and the angle theta A. So this is the real axis intercept, that is the summation of the finite poles minus finite zeros, and the number of finite poles minus number of finite zeros, and angle is given by 2k plus 1 into pi divided by number of finite poles minus number of finite zeros, and the derivation of this can be obtained. It can be obtained, and it is given in the appendix of the textbook that we are following. In this case, k is equals to 0 plus minus 1 plus minus 2 plus minus 3, and the angle is given in radians with respect to the angle is given in radians with respect to positive extension of the real axis. So this is how the rule 5 will tell us that the root locus approaches the straight line as asymptotes as the locus approaches infinity. So from this we can get that that how this infinity poles are at infinity, or poles are zero, can be taken care of. Also, one more point is that k equals to plus minus that is 0 plus minus 1 plus minus 2 plus minus 3. So it yields a multiplicity of lines that account for many branches of the root locus that approaches the infinity. So from this it is clear that this real equation for asymptotes as the real axis is given by summation of finite poles minus finite zeros divided by number of finite poles minus number of finite zeros, and this one angle is as follows. So this is how the finite poles and finite zeros are taken care of. That we can explain this with an example in this lecture in the next lecture. Okay, thank you.